antennas and the greatest unsolved maths problem. Here we'll be looking at simulated radiation patterns, in this case a dipole array. The nulls of the pattern represent the Riemann zeta zeros. In 1737, Euler produced his famous product formula. It used natural counting numbers on the left n and showed there were an infinite number of prime numbers on the right p. Dirichlet extended it to real numbers. His student Riemann further extended it to complex numbers, producing the function's most interesting properties and therefore called the Riemann zeta function. This formula shows the zeta function and primes are intimately linked. In 1859, Riemann wrote his famous paper using the zeta function and introducing his hypothesis. All non-trivial zeros of the zeta function have real part a half. This shows the series form of zeta s, where s is a complex number in this case. For s equals 2, we get the famous Basel problem, publicised by Bernoullis in their hometown. It was solved in 1734 by Euler, who found it to be pi squared over 6. All even integer zeta have been proved irrational or more precisely transcendental. There is no closed form for zeta odd. Zeta 3 was proved irrational in 1978 by Eperi. Riemann looked at the zeta function in the complex plane. This is how it transforms the Cartesian coordinates. He extended it to the whole complex plane using analytic extension. Only one extension has a derivative everywhere. Transformation of this extended function looks like this. This is his equation for the transformed zeta function for the whole complex plane. It has zeros between real part 0 and 1, and Riemann hypothesized all the zeros lie on the line half. If we transform this into the complex plane, we can see how the zeros are formed. This is a contour plot of the absolute value of zeta. The non-trivial zeros are symmetric about the real axis. Y is the height of the zero. The first 10 non-trivial zeros are shown here. The first zero is at a height of 14.1. In 1914, Hardy proved there were an infinite number of real zeros. In 1953, Alan Turing computed over 1,000 zeros. This was the first use of a digital computer to calculate the zeros. By 2020, the number of zeros computed was over 12 trillion. Riemann's result from his paper was an exact formula for pi x, the prime counting function. How many prime numbers are there no greater than x? This gives a step function shown on the right in blue. The zeros are like Fourier components. The larger the height of the zero, the higher the frequency contribution to the πx step, fitting his function ever closer to the steps. This shows how the zeros fit πx. Increasing number of zeros up to 100 here. You can see the actual step is fitted by the red curve, which is his exact formula. In 1900, David Hilbert presented a list of 23 maths problems. The Riemann Hypothesis was number 8 in the list. In a radio interview in 1930, he had no doubt all the problems would soon be solved. He ended the broadcast with his clarion call, "We must know, we will know."
Statt des törichten Ignorabimus heiße im Gegenteil unsere Losung: Wir müssen wissen, wir werden wissen.
This is his epitaph. The Riemann hypothesis now attracts $1 million for its solution. In 1947, van der Pol used an electromechanical method to visualize the Riemann zeros. The Fourier transform of his sawtooth function shows the Riemann zeta zeros. He used a rotating paper disc with the van der Pol function imprinted as teeth, modulating a beam of light incident onto a photocell, and then with an ingenious use of varying sinusoidal current, produced the mechanical Fourier transform shown with dips at the Riemann zeros. Since the far-field radiation pattern of an antenna is the Fourier transform of its aperture field, Berry suggested the zeros may be seen as the pattern nulls. An antenna has a finite aperture, and so the function will be truncated. This affects the visibility of the nulls, shown here for u equals 3 to 15 and infinity. A compromise for visibility of the zeros is u max greater or equal to 3. Simulated antenna designs. This is a dipole at 40 GHz. We start with a dipole array. 601 dipoles are separated by 0.8 mm. U max equals 3. The feeds are given the van der Pol voltage. These are the simulated radiation patterns. Various views are seen. This pattern cut will show the zeros. This is the pattern. The first null is the first zero at 14.1. The visible limit on the height of the null for this design is about 67. This gives the zero to within about 1% error. But this is not a practical design, since it would be difficult to feed the dipole array. A more practical design: slots in the ground plane diffract a plane wave. 601 slots of 0.8 mm spacing. Umax is 3. 37 micron thick ground on a PCB substrate, e.g. duroid. 500 mm length. Minimum slot dimension is 30 microns. This shows the electric field just above the slot. Electric field amplitude at the slot centers approximates the required function. This shows the patterns at 40 gigs. Again, the zeros are visible in the cuts, up to a height of about 65, with about 1% error. To try and see zeros at greater height, we could look at a longer slot array. It may be possible to join 3 500mm boards. We could use a low density foam, e.g. roller cell, to support them. 1601 slots separated by 0.8mm, Umax 3. Zero height increased to 208. Probably the largest antenna that could be tested in a Qatar. These are the patterns at 40 gigs. There's more nulls seen now. The first 84 zeros are visualized. The nulls are now closer together. Some are difficult to see. Visible up to a height of about 108. So the conclusions then. Simulated antenna designs can show the Riemann zeros. They appear clearer than expected for Umax equals 3. The first 84 zeros are visualized. The visible zeros are up to a height of about 208 with 1% error. The slot design is manufacturable, but the difficulty is how to measure this design. Interest in the Riemann hypothesis continues. Since we have seen the zeros are linked to prime numbers and prime numbers are useful. The use of prime numbers. In 1940, Hardy at the age of 62 wrote an autobiography. In it, he said, "I have never done anything useful." But he didn't foresee online banking or WhatsApp. But he did write a book on number theory used by the British mathematician. In 1973, he produced a public key cryptography algorithm using prime factorization. It was independently invented in 1978 and known as RSA.